section 16.6, which deals with surface area. Before we do that, in the last lecture things were getting a bit tedious and tape was getting a little bit long, and I said the very last 3 problems I would address in class today. So let's look down here. The one that we were looking at the end of the period last time said use polar coordinates to find the volume above the cone z equals square root of x squared plus y squared, and below the sphere x squared plus y squared plus z squared equals 1. Now the cone z equals square root of x squared plus y squared is going to be going along the z-axis. He's going to be coming up like this, okay? And the sphere is a sphere of radius 1, so I'm going to take a sphere of radius 1 and think of your sphere coming down like this, and it does go all the way down here. But the region that we're talking about is the region that is above the cone but below the sphere. And we want to figure out the volume of it. Now let me just preface here. When you're doing these double integrals and you were taking, you know, your f of x, y, dx, dy, or you did it in polars or whatever, always, always, always what happened here was you had some region in the xy plane and you had some surface above that, and then you thought of having like perpendiculars coming up, and this might be like this when I take my perpendiculars up. And what we wanted to find was the volume that was underneath this surface above that region in the bottom. Each time when we did this double integral, in reality what you were doing is you were summing up f of x y's times delta x delta y's. And what were these? Well, if you took this region and partitioned it like this and like this, each of these things that I was summing up was a height times a width times a depth, right? Because if I took like one particular little delta A right there, that up here would have like a sister little region right up here, and we're trying to find what that volume is of that little parallelepiped, that little rectangular solid there. So the point is this: the whole idea is you're taking height times width times length. Now what makes this problem a little bit more difficult is that you don't really have a base, but if you notice, these two curves are intersecting, or these two surfaces are intersecting right here along that little circle. And if I want to find the volume of it, if I could like to consider this as my base, because if I partition that as my base and I break them up into little pieces, each little point that I take, you see, the height of that little rectangular solid would be the distance from here down to here. You with me? And what I like to do is if I look where these guys, so whenever you want to find a volume and you've got a problem like this, look to try to find your region where if that's your think of that as your base. If you look above and then below, no matter what point you pick on that base, you're going to be going always with the same surface at the top with the same surface at the bottom. And if I think of a little delta A region right here, you could have your little delta A here and your little delta A here, and you look at it, that little delta volume would be my height times my dA. And what's my height? My z on the top minus my z on the bottom times delta A. With the two surfaces that we have, the top surface was real easy. It's the sphere. So it's given by z squared equals 1 minus x squared minus y squared. Or the sphere is given by z equals square root of 1 minus x squared minus y squared. That's my sphere. And the cone, they already gave me the equation. It's z equals square root of x squared plus y squared. Okay, so these are in fact, this is the top, and this is the bottom. All right, so what's the integral that I'm going to set up? Well, the integral that I'm going to set up, first of all, what I like to do is I got to figure out what's the equation for that circle. And notice, if I take that circle, I actually can project it down onto the xy plane. Well, let's see, that would come down to about here. Okay, and you've got some circle that's down here that is the shadow of this circle that's here in the xy plane. Well, how can I get it? Well, very easily. The one equation is given by z equals square root of x squared plus y squared. And the other equation is given by z squared equals 1 minus x squared minus y squared. If I square both sides on the cone, I get z squared equals x squared plus y squared. So I have z squared for the cone is equal to this, and z squared for the sphere is equal to this. Well, this little circle, those points are on both the sphere and the cone, so I can set them equal to each other. Add x squared on both sides, add y squared on both sides, and I end up with x squared plus y squared is equal to a half if I divide through by 2 on both sides. So this circle that they intersect on is the circle x squared plus y squared is equal to 1/2. That's this little circle right here, which I projected down to here. Okay? Now, if we're going to go to try to find that volume, my height is going to be z on the top minus z on the bottom times delta A. And we already got those equations, so let me just pull them back. They're right here. My sphere on the top is square root of 1 minus x squared minus y squared. That's a minus there. Minus my cone is square root of x squared plus y squared, dA. And what's the region that we're integrating over? Well, we can integrate over this region right here, or we can take that projection down onto the xy plane. And we already figured out the equation of that intersection was given by x squared plus y squared is equal to a half, which is a very nice little circle. It's a circle with r squared equal to a half, or r equal to 1 over root 2. And I think to me, this, if I'm integrating over that circle, and we are on the region that deals with circular regions, polar coordinates, let's do our integration in terms of r's and thetas. And so my integration is going to be square root of 1 minus r squared, because x squared plus y squared is r squared, minus, this is square root of r squared. For dA, I'll put in r, dr, d theta. What's my r ranging from? My r is ranging from 0 to 1 over root 2. And my theta is going from 0 to 2 pi. I'm not going to do this integration because it's a pretty simple integration to do. I would break it up into 2 integrations. This one's going to be a u substitution. Notice if you break them up, the one turns out to be 1 minus r squared to the 1/2 times r, dr, and the other, square root of r squared is r, times r is r squared dr. That's simple algebra. That's a Calc 1 problem. This is almost a Calc 1 problem too. It's a u substitution with your u equal to 1 minus r squared, and then taking it from there. Okay, so part of your assignment is to finish it from that. But the hardest part, I think, is realizing that you've got to figure out where would be my platform, so that when I go my height, what's my height? I look above and I look below, and I'm going from here down to here. And that's going to be my height of my little parallelepiped, and this is my little dA. Okay. All right, there's 2 more that I skipped because of lack of time. So let's look at those quite quickly. In this one, a lot of times, it's much easier to do an integration, especially if the region is circular, to change it to polar form. All right, so it says evaluate the iterated integral by converting 2 polar coordinates. Well, notice in this one right here, in my inner integral, x is ranging from 0 to x equals square root of a squared minus y squared. And then my y is ranging from y equals minus a to y equals a. Now these are constants, minus a and a. But this one you go, ooh, I have no idea what that looks like. Well, x equals 0, I know what that looks like. And this one, to get a sense what he looks like, let's square both sides. Add an x squared, a y squared on both sides. And heavens, what is that? That's a circle of radius a, except the original equation only has x equal to positive square root. So we're not getting the whole circle, are we? We're only getting the positive x. So instead of drawing a whole circle, because there x would be minus the square root, This is x equals square root of a squared minus y squared. So x is ranging from, you take an arbitrary x and it's going from 0 to that region, 0 to that region. But then the y's, they tell me, are ranging from minus a up to a. So that's what my region looks like. All right, so now we're ready to do our integration. First of all, I'm going to replace x squared plus y squared with r squared. So I'll have r squared to the 3/2. I replace the x dy, you might remember from last time, with r dr d theta. Okay, and now what's my r ranging from? Well, if you take an arbitrary spoke, what's your r ranging from? It's going from 0 to a. This is a circle of radius a. And then my theta, what's your theta ranging from? Well, if this is theta equals 0, right, that's theta equals 0. If I rotate him down to here, like rewinding, what's that theta going to be? Minus pi over 2. So we're going to go from minus pi over 2 to 0 to pi over 2. So you're going to be going from minus pi over 2 to pi over 2. And so rewriting this a little bit, it would be the double integral from 0 to a. R squared to the 3/2 is r cubed times r is r to the 4th dr d theta. And again, I'm not going to do this integration. You consider a to be a constant, and you should get the answer that I have on the sheet there for you. Okay, I just wanted to go over changing the limits of integration. Okay, the next one I want to look at, that I thought you guys were getting a little bit too tired, I thought it'd be best to wait for another day, is this one. And this one is very nice because it deals with polar coordinates that we might have forgotten. In this one, again, they want us to change it to polar form, and notice my y is ranging from y equals 0 to y equals square root of 2x minus x squared. Now they want me to change that to polar form. This is y equals 0, that's easy enough. This one, if we square both sides, we get y squared equals 2x minus x squared. Now there's two ways that I can figure out what that looks like. Okay, one way is if I look at it, I could throw everything to the one side. Okay, I added x squared and I subtracted 2x. I could complete the square on this baby. And to complete the square, to make this be a perfect square here, I need to take the coefficient of x, which is 2, divided by 2 is 1, square it. I need a 1 here to make this be a perfect square. So I'll add another 1 on that side. And so this is just quantity x minus 1 squared plus y squared equals 1. What is that? That's a circle of radius 1, and where's its center? Its center's at 1, 0, and its radius is square root of 1, which is 1. So this particular circle that they're talking about has a center at 1, 0, and the radius is 1. So I can go to the right 1, to the left 1, up 1, down 1. This is what the circle looks like. Going back and using rectangulars. Now, if you're a little bit comfortable with polars, let me do it with polars also, because I think it'd be good. Since they say put this in polar form, well, notice, if, just reviewing from last time, when I do something in polars, the substitutions that I'm doing are, I let x equal r cosine theta, y equals r sine theta, and x squared plus y squared goes in for r squared. And in addition, your dA, which was dx dy, becomes r dr d theta. All right, so here I go, oh, look at this. X squared plus y squared is 2x. So for x squared plus y squared, I can put in r squared. For x, I can put in r cosine theta. And this dividing by r gives me r equals 2 cosine theta. And if you put your calculator in polar mode and had it graph it, you would get that lovely little circle there. So this is r equals 2 cosine theta. Now, I didn't finish my region. My y is ranging from 0 to this. So where is y is 0? Here's y equals 0. And then we're going up to y equals square root. That's only positive. So my y's are going from here to here, here to here. And then what x's are we ranging? We're adding up our x's from 0 to 2. So if you add up x's from 0 all the way to 2. I'm just getting the top half of that circle, the semicircle. So now we're ready to do our integration. And our integration is going to be the double integral, where I see x squared plus r squared, x squared plus y squared, I put r squared. Where I see dy dx, I put r dr d theta. And now let's see. We don't even have to look at these. We say to ourselves, okay, take an arbitrary spoke. Okay, an arbitrary spoke in that region. What is r ranging from? Well, here it's r equals 0, and in the end, it's r equals 2 cosine theta. Okay, and what are my thetas ranging from? Well, here it's obvious that it's theta equals 0, but we have to check. What do you think this is? I think it's probably pi over 2, and let's check. If theta is pi over 2, r is equal to 2 cosine of pi over 2. And what's the cosine of pi over 2? 0. You also could put that on the calculator and use your little trace key going from here to here, to make sure that that's the first theta that makes you back at the origin. And again, so we're going to pi over 2. So this is equal to the double integral from 0 to pi over 2, 0 to 2 cosine theta. Square root of r squared's r times r is r squared dr d theta. And again, I'm not going to go through and do this. We did a bunch of them the other day. I can just tell by looking at it, you're going to end up with a cosine cubed in this one. And in fact, let me just mention this, in fact, just to save us a little bit of time. But I can guarantee you, you're going to get to the point, I'm not going to do the whole thing, but if I would do this, but you're going to get to a point where you're going to have an integral of cosine cubed theta d theta, guaranteed. If you go through and do this, you're going to get that. How do I integrate a cosine cubed theta d theta? How do you do that? Because this is, a lot of this is bringing stuff back from calculus, too. You siphon off a cosine. If I siphon off a cosine, the cosine squared I replace with 1 minus sine squared. And then you're going to do a simple u substitution, u equal to sine theta. So du, derivative of sine, is cosine. And this integral is going to become the integral of 1 minus u squared. And the cosine theta d theta is going to be du. And you'll have a simple algebraic thing to do. And just don't forget, after you get it in terms of u's, you've got to go back and plug back in your thetas. Okay? All right, today we're going to go on and talk about surface integrals. Those of you that did not print out these sheets, don't frantically try to copy this, all right? I just want to talk for a few minutes. What we're doing is I have a particular region R. I chose it just to be easier to do it on Maple. I have this little region R that's in the xy plane. And what I'm doing is I take little perpendiculars, perpendicular to the xy plane, and shoot them perpendicular up to the surface S. Okay? And when I do that, they're coming up along here. And where are they intersecting? They're intersecting the surface, producing this little piece of the surface z equals f of xy. And our job today is, what is the surface area of that? If I wanted to carpet it, how much carpet would I need to cover it? If I wanted to paint it, what's the square footage? Okay, that's what we're trying to figure out. The surface area of the part of the huge surface that's limitless, that's just above this fixed region R that I'm choosing. Now, first of all, it curves. You know, it's a curved kind of thing. So how are we going to get a handle on how we can approximate what that surface area is? Well, first of all, notice what I did is I took my region R and I broke them up into a bunch of little DAs. And by the way, just sit back and enjoy the show. I don't want you frantically copying notes, okay? And I'm taking one particular DA right here. Okay, it's right there. And I'm shooting it up perpendicular to the xy plane. And we get this little surface right here. Now this little surface curves, but he doesn't curve as much because it's a little delta S, little delta surface. And I'm thinking, how can I get a handle on what is the area of that surface? I'm going to use a little bit of what we've done in previous chapters. At this point right here, I'm finding the tangent vector. And I'm extending it till it hits that little post right there. This is the tangent vector as x changes. And this is the tangent vector as y changes. Now he's not going to be exactly on the surface. It's tangent to the surface. But if your delta A is very, very small, that's going to be very, very close to the surface. And what I'm going to do is I'm going to construct the plane by drawing a parallel to this vector over here and a parallel to this vector over here. And that's what I'm showing in the next picture. And as you can see, I did this on maple, so it's done very exactly. But I drew a parallel to this vector here and a parallel to this vector here. And as you can see, this little plane that's right here, it's not exactly equal to that surface. It's off by a little bit. You can see that little gray bit there. It's off by a little bit. But as delta A gets smaller and smaller and smaller, the area of that plane will be incredibly close to the area of the surface that I get by bringing up these things. Now, I don't know if you remember this or not, but back in, I think it was chapter 13, if you had a vector A and you had a vector B, and we wanted to talk about the plane that was determined by vectors A and B, does anybody remember the formula that we had for the area of that surface, of that plane, of that little parallelogram?
Absolute value of A times absolute value of B.
But it's cross. It's cross product. Remember, you had to take the cross product of A cross B, and then, very good, and the length of that vector. Excellent. Okay? Part of the reason we did that was because we're going to be using that in this chapter and in the next chapter also. All right? So, all I have to do, and you say, yeah, I'm glad you're doing it, Mrs. Strocko, and not me, right? But I have to figure out this vector and that vector. And how can I represent those vectors? All right? Now, my next picture here is this. Now, what I've done, notice, along here, you see this curve right here? Y is fixed, and X is changing. Y, we'll say this point right here is X naught, Y naught. That's down right here. And then this, of course, is X naught, Y naught, Z naught. But we're fixing Y equal to Y naught. We're not letting Y change. And so we're looking at this curve right here where Y is fixed at Y naught. So if Y is fixed at Y naught, I actually took that curve on maple and graphed it right here. Now this is the slice with Y fixed at Y naught. You follow? And so I'm just drawing my little XY axis right here. You follow? Parallel to the X-axis, parallel to the Y-axis, but having it actually go through the point X naught, Y naught. You with me? Now, the vector I want to come up with is this baby cakes right here. Because you see, this is your delta X that's projected down onto the region. And the vector's starting at the one point, but it's got to go the full width till it gets to the other. And as you can see, it's off a little bit from the surface because the surface curves and the vector's straight. Now, I think you might remember, or you might agree, that the partial of z with respect to x is approximately equal to delta z over delta x. Are we all okay with that? As long as delta x is small, they're incredibly close. So delta z is real close to the partial of z with respect to x times delta x. All right? Now look at this vector right here. Look at this lovely vector I have right here. This vector has a z component and an x component. And what's its y component? 0, because y is not changing. Y is fixed at y naught. All right? So this vector, which I'll call him A, is equal to its x component is delta x times I, its y component is 0 times j, and its z component is plus delta z times k. Because you got your, and in this particular case, the delta z is negative, but that's fine. Delta z will take care of it. So therefore, vector A is equal to delta xi plus, and I'll write it as the partial of z with respect to x times delta x times k. And that's this little tiny vector right here. Or better yet, this picture looks a little bit better. This one right here. That one right there I could represent as the x component is delta x, the y component is 0, and the z component is partial of z with respect to x times delta x. And we're evaluating partial of z with respect to x at the point x naught, y naught. But you get the picture. Okay, now, I could have done the exact same thing, but I'm not going to. And I could have drawn this curve. Okay? That curve right there has x fixed at x naught. And we're going to be talking about the partial of z with respect to y. And through the exact same thing that I did here, I can represent this vector as 0 delta y, partial of z with respect to y, delta y. Okay? Now you guys just told me if I wanted to make that little plane right here and find the area of the plane, you told me, Mrs. Strocko, take the cross product and then take the length of that vector. Right? So let's do it. We want to take the cross product of the vectors. The first one has an x component of delta x, y component of 0, z component is it okay if I write, I'll write it as partial of z with respect to x, delta x. All right? The other one, y component is 0, x component is 0, y component is delta y, z component is partial of z with respect to y, delta y. To find the cross product, we'll just call this as A cross B. This one being vector A, this one being vector B. So let's see, A cross B is going to equal I times, we eliminate the row and column that I is in, and we get 0 minus partial of z with respect to x, delta y. Then we go minus j, eliminate the row and column that j is in, and I get partial of z with partial of z with respect to y, delta y, if you like to write things alphabetically, plus k times, eliminate the row and column k's in, you just get delta x times delta y. Now is it okay, each of them has delta x, delta y, so is it okay if I factor that out? So I'm going to get minus partial of z with respect to x, I, minus partial of z with respect to y, j, plus 1 times k times delta x, delta y. Now delta x, delta y is a number, right? How much x changed, how much y changed. It's the area of that little delta A area. Now, the area of that little parallelogram is the length of that vector, and the length of that vector is equal to, since this is a constant, I can just factor it out. Is that okay? And I get, how do you find the length of the vector? Take the x component and square it, plus the y component and square it, plus the z component, and 1 squared is 1 last time I looked. And then I got delta x, delta y. Okay. What's the problem? dz, yes, I apologize. Yes, because that's partial of z with respect to y. Now that was just that one itty bitty little area. But if we add them all up in the x direction, in the y direction, and take the limit as delta x and delta y go to 0, this becomes the integral over region R. What's region R? The projection of the surface down onto the xy plane of the square root of, instead of writing it as partial of z with respect to x, why don't I write it as f sub x squared, partial of z with respect to y, fy squared plus 1 dx dy. Isn't that cool? Time for notes. The area of the surface with the equation z equals f of xy, where xy are xy are the points that are in D in the xy plane, and where fx and fy are continuous first partials, is given by, I don't like this notation, this is area of surface. Now notice, your surface is up here, but your region down here, and then you just take your little projections up here, and you've got like, and that's the surface area that you're taking. But the way I think about it is, think of the sun being up here, and the sun's shining down. This is the shadow onto the xy plane, and you're integrating over the shadow. And it's a very simple integral, square root of fx squared plus fy squared plus 1 dx dy. Now I think this section is incredibly easy because you don't even have to picture what they look like. You just have to figure out what the shadow is. Okay, and that's the region that you're going to integrate over. So let's do a few of these before we call it quits today. First one, it says, find the surface area of the part of the surface z equals x squared plus 2y that lies above the triangular region T in the xy plane with vertices 0, 0, 1, 0, and 1, 1. You don't even have to picture what it's looking like. Instead, draw the shadow. The shadow's in the xy plane. The xy plane, it's a triangular region that has 0, 0, 1, 0, and 1, 1. Now, the keys to the kingdom with this problem is, which way do I integrate? Those of you that say, oh, I always go dx dy, your life's going to be a little bit more difficult than those that can be a little bit more flexible. Next thing, you say, okay, surface area, Miss Strocko, piece of cake. Surface area is double integral square root of, that pen's dying, so I think we'll throw him out, square root of 1 plus fx squared plus fy squared dA. So you have to look at f. Here's your f. F is what z is, the surface, x squared plus 2y, and figure out what fx is. That's just 2x. And fy, partial with respect to y, is just 2. So playing plug in here, I get square root of 1 plus fx squared is 4x squared, and fy squared is 4 dA. Are we all okay? Now, simplifying this a little bit, I get square root of 5 plus 4x squared dA. Which way do you guys want to integrate? With respect to x first or with respect to y? You integrate with respect to x first. If you make this be a dx, okay, so let's let it be a dx here. How do you substitution's not going to work, people. You're going to have 5 plus 4x squared. U is 5 plus 4x squared. Du is 5 plus 4x squared. Du is going to be 8x. I don't see an 8x there. I don't see an x dx. It's a trig substitution that you need to do. Those of us that don't flinch and say trig substitution, I can do that just fine, then you're more than welcome to do it that way. But instead, let's try integrating dy dx instead. If you integrate dy dx, that inner integral is going to introduce an x. So the integral I'm going to want to do is 5 plus 4x squared dy dx. And my picture,
To the 1/2, Miss Strocko.
to the 1/2, thank you. Definitely to the 1/2. Square root is a 1/2. Now, if I'm integrating with respect to y first, pick an arbitrary x. What is y ranging from? Well, it's obvious y is ranging from 0 to, and what's this line? That's just y equals x. So y is ranging from 0 to x. And if we add all those up, your x's are ranging from 0 to 1. And look how nice this is. Let's do our inner integral first. Doing our inner integral first, we're going to go integral from 0 to x of 5 plus 4x squared to the 1/2 dy. This is just a constant, isn't it? That's just a constant. So it's going to be 5 plus 4x squared to the 1/2 times y, as y goes from 0 to x. And you're going to plug an x in for y. And when you plug in a 0 for y, you just get 0. Isn't that nice? So you get this. And I'm going to take this and plug him in to the outer integral. And the outer integral is integral from 0 to 1 of 5 plus 4x squared to the 1/2 x dx. And now what am I going to do? U substitution. Piece of cake. I think I'm going to let my u be 5 plus 4x squared. So du is 8x dx. If you don't like putting the 8 here and the 1/8 here, you can multiply by an 1/8 on both sides and say 1/8 du is x dx. So where I see 5 plus 4x squared, I put u to the 1/2. where I see x dx, I replace it with 1/8 du, and this is going to equal 1/8 times u to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. 2 goes into 8/4, so that's 1/12. And what's u? 5 plus 4x squared to the 3/2, and we're going from x equals 0 to x equals 1. Okay, and let's see. If I plug that in, if I have a 1/12, I just like to factor him out to the front. Pop in a 1, 5 plus 4 is 9. 9 to the 3/2 is take the square root of 9 is 3, cube it is 27. Minus, put a 0 in here, you get 5 to the 3/2. And that answers just fine. But notice you can write 5 to the 3/2 is 5 to the 1 times 5 to the 1/2. So your book likes to do it as 27 minus 5 root 5 is your answer. Nice little problem. Not hard. Okay, let's do another one. Find the surface area of the part of the plane 2x plus 5y plus z equals 10 that lies inside the cylinder. X squared plus y squared equals 9. Now I said you really don't even have to see what the picture looks like, but x squared plus y squared equals 9, everybody in here should know, is a circle of radius 3. Okay, so we can go like this. And it comes up like this. Now I'm not sure I'm not going to draw that plane exactly, but think about a plane coming up and slicing the cylinder. It's going to slice it somehow, maybe like this. And what we want to do is we want to get that surface area. Now, notice the shadow of that plane, even if part of it's below the xy plane and part of it's above, the shadow is the cylinder on the xy plane. You with me? So we're going to go double integral square root of 1 plus fx squared plus fy squared dx dy or dy dx, or we can say dA, over that circle R. That's the circle. Now we got a few things that we have to figure out first. First, we got to get this fx and this fy. Where do they come from? They come from the equation of the surface, z equals f of xy. In this particular case, my surface is z equals 10 minus 2x minus 5y. That's my surface that I'm finding the surface area of. So my fx is a negative 2, and my fy is a negative 5. Okay, so my integral, which is square root of 1 plus fx squared plus fy squared dA, is going to be square root of 1 plus fx squared is 4, fy squared is 25 dA, which gives me square root of 30 dA. Now, what's the region that I'm integrating over? The circle. Okay? The region R that I'm integrating is the circle. X squared plus y squared is 9. A good mathematician is a lazy mathematician. That's a constant. I can factor him out. If you integrate over a region and your integrand's a 1, what does that integral give you? This integral, if it's just a 1, you're going height times length times width. Well, the height's 1, so you just get length times width. You're just getting the area of the region. So this is equal to the area of the circle. Do I need, we could, people do our, we could have done this in polar coordinates and been real pleased and all that, but why bother? I think I know what the area of a circle is. It's pi r squared. And the area of the radius of that circle is 3. So it's square root of 30 times 9 pi, or I guess your book likes to write it as 9 pi root 30. Do you follow what I just did? The double integral, when your integrand is 1, that dA, just think about it. What are you doing? When you're going integral over region dA, remember these are double summations. And you've got your region R here, and you partitioned them up into a bunch of little pieces. Well, for each little one, you're going 1 dA. All you're adding up is the delta A's. You add up all those delta A's, and you have your region. Now we could have, but I didn't want to. You could have done this instead. I could have changed the dA to r, dr, d theta, and you could have said, oh, what does arbitrary r range from 0 to 3? And if I add up all of those, what's my thetas ranging from 0 to 2 pi? And if you finish that, you're going to get the exact same answer. But I have no problem. If you have an integral that's representing the equation of the area of a circle, use geometry, for heaven's sakes, and save yourself 5 minutes. Okay? All right, we got another one. Next one we want is find the surface area of the part of the surface z equals 1 plus 3x plus 2y squared that lies above the triangle with vertices 0, 0, 0, 1, and 2, 1. Okay? All right, so first of all, we want to get our fx and fy first. Z, which equals f of xy, is equal to 1 plus 3x plus 2y squared. So fx is 3, and fy is 4y. So square root of 1 plus fx squared plus fy squared is equal to square root of 1 plus 9 plus 16 y squared, which is square root of 10 plus 16 y squared. You all okay with that? That's going to be our integrand. Now our region has vertices 0, 0, 0, 1, and 2, 1. So my vertices, I'm just going to draw them right here. 0, 0, 0, 1, and 2, 1. What's the equation of that line right there? Y equals 2x? Check. If you multiply x by 2, you get 4. It's a half x. Right? Y equals a half x, because if you take 2, multiply it by a half, you get your y. Right? Okay. And the region I want to integrate over is this part. So we're integrating square root of, I just figured out the 1 plus fx squared plus fy squared was 10 plus 16y squared. And we can integrate with respect to y first or with respect to x first. What do you think you want to do? I think I'm going to go with respect to x first. Because if I went with respect to y first, I'm looking at this and I go, ooh, that's going to be a trig substitution, which is fine. But I mean, if you don't have to do it, why do it? So we have to decide now if you pick an arbitrary x, fix y, fix an arbitrary y, and let x vary. X is going from here to here. So x is ranging from 0 to what? Well, I got to have what x is ranging from.
0 to 1.
Yes, you got to take this equation and solve for x. Because it's saying, what is x ranging from? From 0 to here, x is 2y. Okay, and then if we sum up all those y's, the y's are ranging from 0 to 1. Okay, we all okay? What's wrong? Did I lose you? Why this had to be x is 2y? Okay, because x is ranging from, we have to know x equals what to x equals what. Here, no problem, x is 0. Here, the equation was y equals 1/2 x. If I want to know here what does x equal, I have to multiply by 2 on both sides to get x is 2y. Okay, let's do the inner integral first. It doesn't look too hard. We're going to go the integral. X goes from 0 to 2y of 10 plus 16y squared to the 1/2 dx. Piece of cake. That's a constant in terms of x. So it's going to be 10 plus 16y squared to the 1/2 x, right? Because it's like a 5 dx, so it's just like 5x. As x goes from 0 to 2y, which gives us 10 plus 16y squared to the 1/2 times, popping a 2y in for x, and then you go minus, popping a 0 gives you 0. So this is my inner integral. Now I have to take that and plug that in into my outer integral. Plugging it into my outer integral, I now have the integral from 0 to 1. Is it okay if I pop that 2 out front? 2, 10 plus 16y squared to the 1/2 y dy. The 2, I just put him out front here, so I don't have to deal with him. And this just cries out. How do you do that integration? U substitution. I'm going to let u equal 10 plus 16y squared. Du is 32y dy, or 1 over 32 du is y dy. So I get 2 integral as y goes from 0 to 1. U goes in for that. And for y dy, I'm going to put 1 over 32 du, which gives me 1/16 times u to the 3/2, dividing by 3/2 the same as multiplying by 2/3. 2 goes into 16 18 times, so I have 1 over 24, 10 plus 16y squared to the 3/2 as y goes from 0 to 1, which gives me 1 over 24, which I like to factor out. Popping in a 1, 16 and 10 is 26. And again, 26 to the 3/2 you could write as 26 to the 1 times 26 to the 1/2 would give you 26 times root 26 minus, popping in 0, you get 10 to the 3/2, which is nice to write as 10 root 10. And there's our final answer. Everybody okay with what I did here with 26 to the 3/2? We're okay? What I did is I had 26 to the 3/2, which is 26 to the 1/2, which is 26 to the 1st times 26 to the 1/2, which is 26 times root 26. And the same thing with the 10 to the 3/2. Okay, I think we just have one more. So let's look at it. Am I lying, or is it 2 more?
1 more.
It's 2 more. I love it in my profession. Any other profession, you know, if I was selling donuts, you know, and I say, you know, you got to pay $6 for a dozen, and if I gave you 10, you'd be yelling, "What? Where's my 12 donuts? I paid for 12 donuts." Where when you teach, you know, if you say, "I'm going to do 10 problems," and you do 6, nobody asks where the 4 is that they paid for. You know, they're perfectly happy just to have the, you know, give me half of what you want to give me. Yeah, get to the donut shop. Okay, me too. All right, I love this one, so let's do it. Find the surface of the part of the paraboloid z equals 4 minus x squared minus y squared that lies above the xy plane. Now the reason I like this problem, we could go, oh yeah, Miss Strocko, my z, which is my f of xy, is my 4 minus x squared minus y squared. So my fx is minus 2x. My fy is minus 2y. So my square root of 1 plus fx squared plus fy squared is square root of 1 plus, that squared is, oh, you can't see that. Let me move it up a little bit for you. 1 plus 4x squared plus 4y squared. So that part's easy. Okay? Now, what's my region I'm integrating over? I got a paraboloid. They just want the part of the paraboloid that lies above the xy plane. What does that paraboloid look like? Is he an upsy or a downsy? He's a downsy, isn't he? Because it's 4 minus. So he's going down like this. We got to figure out this region right here, because that's the region that we're integrating over, because we just want the part of the paraboloid that's above the xy plane. Well, since it's z equals 4 minus x squared minus y squared, on the xy plane, I think all of you would agree z equals 0. If I put a 0 in for z, I get x squared plus y squared is 4. So that region right there in the xy plane is the circle. It's a circle of radius 2. 1, 2, 1, 2, 1, 2, 1, 2. That's our region R that we're integrating over. So, taking that on the side, I'm integrating to find my surface area. It's going to be the double integral of the square root of 1 plus 4x squared plus 4y squared dA, where A is that lovely region. How do you think we should do this integration? Polars. Absolutely. You've got to do polars. You're invited to do it without polars. I mean, it is a pain. I taught out of textbooks one time that made you do all this stuff without polars. And then when they got to the polar section, the students were like, oh, thank goodness, because, I mean, it's pretty office. But now watch here. I can write this as 1 plus 4 quantity x squared plus y squared. And for dA, I'll put in r dr d theta. And so this becomes double integral of square root of 1 plus 4r squared r dr d theta. That's beautifully in polars. Now, what's my region? Well, this is the simple little circle of radius 2. So if you take a simple r, what is your r ranging from? From 0 to 2. And if you have to add up all those spokes all the way around, 0 to 2 pi. This is not a hard one to do. I don't think I'm going to go all the way to the bitter end. You can try to do it at home. But at home, let's just talk for a second. If you do it at home, and we do it on that inner integral, how are you going to handle that integral? Use substitution. What's nice is Calculus 3 does make us remember what we did in the past. So your du is 8r dr. So 1/8 du is r dr. So this is going to become the integral of 1 plus 4r squared is u to the 1/2, and r dr is 1/8 du. I might as well finish it. I get 1/8 u to the 3/2 and 2/3, which gives us 2/24, which is 1/12, and u is 1 plus 4r squared to the 3/2, and we're going from 0 to 2. So if I factor out the 1/12, you pop in a 2. 2 squared is 4. 4 times 4 is 16, plus 1 is 17. 17 to the 3/2 is 17 root 17. Put in a 0. 1 plus 0 is 1. 1 to any power is 1. Now that's just my inner integral, but that's one nasty constant. So if I put that into my outer integral, you guys tell me, what can I do with my constant? Drop kick him out front. The integral of d theta is theta. And if you go from 0 to 2 pi, you end up with this times drop in 2 pi minus drop in 0. And I guess I can write this as 2 pi over 12, which is pi over 6, 17 root 17 minus 1. Okay, nice problem. Now this is the last one. This was the penultimate. That means next to last. Now we're at the last. Okay? All right. Find the surface area of the surface z equals xy that lies within the cylinder x squared plus y squared equals 1. This is my surface. This is my region. Okay? So my equation is z is f of xy is x times y. So f sub x is y, f sub y is x. So my square root of 1 plus fx squared plus fy squared is square root of 1 plus y squared plus x squared. And the region that we're integrating over is this simple little circle of radius 1. So we have the double integral of square root of 1 plus y squared plus x squared dA. But whenever you have a circular region, polar coordinate time. R dr theta. And my r is ranging from 0 to 1, and theta is ranging from 0 to 2 pi. And x squared plus y squared, that inner integral, x squared plus y squared is r squared. All right, and how are we going to do that integration? I think we're going to let u equal, we'll let u equal 1 plus r squared. So du is 2r dr, or 1/2 du is r dr. That sounds like hardy hard. All right, and bringing him down here, this becomes 1 plus r squared was u, so this is u to the 1/2. And for r dr, we put in 1/2 du. And so this is going to give me 1/2 u to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So I have 1/3 times 1 plus r squared to the 3/2. And that inner integral went from 0 to 1. So this is equal to 1/3 times, you pop in a 1. 1 plus 1 is 2, so it's 2 root 2. Pop in a 0 is you get minus 1. Okay, and then for the outer integral, popping this in, we just have 0 to 2 pi. What was my inner integral? Just a constant. 1/3 2 root 2 minus 1 d theta. You can drop kick this out front. That's going to give me 1/3 2 root 2 minus 1 theta. Pop in 2 pi, pop in 0. You'll get 2 pi, and you could write that as 2 pi over 3 times 2 root 2 minus 1 is your final answer. Now, this is the last one, but I do want to make one little comment. For your homework, I'm not done yet either. For your homework, I want you to read pages 1055 to 1057. And then on page 1057, only 5 problems, 1 to 9, the odds. Now, before we close, when you get to number 5 in your homework, I'm not going to draw the region. I'm not going to do the integration. You're going to get an integral, if you do it correctly, that looks like this. Okay, so forget that part because you're doing the inner integral. Square root of 1 over square root of 9 minus y squared. Trig substitution, people. You might want to go back and review your trig substitution. With this one, you're going to let y equal, remember when it was in the form of a squared minus x squared, you let x equal a sine theta. So that your y is going to be 3 sine theta here. So your dy is going to be 3 cosine theta d theta. And you might remember what's underneath that radical becomes 9 minus your y is 3 sine theta squared, which is going to give you square root of 9 minus 9 sine squared theta, which is going to give you square root of 9 times 1 minus sine squared theta. And what's 1 minus sine squared? Cosine squared theta, which will give you 3 cosine theta. But I just thought that helpful hint might be helpful. All right, have fun just doing 5 homework problems instead of 27,000, and I'll see you next time.